Are there any questions? Okay, great. Let's go ahead and keep going. So we're going to move on today. We're going to talk about, we've talked about balancing equations. One thing we haven't talked about in terms of writing equations is phases of matter. Okay, so let's see, what do they call them? They call them phase symbols in your book. So we're going to talk about phase symbols. Indicate the state of matter, mostly. All right, in chemistry, we're really only concerning ourselves with 3 states of matter, but so S is going to, if you have something that looks like an S, that means that it's a solid. If we have an L in parentheses like this, that means it is a liquid. If we have a G in parentheses, that means it's a gas. And then the other thing we do, which is not an actual state of matter, is aqueous, which means dissolved in water. AQ. Dissolved in water. All right, we're going to see today that for ionic compounds, this is special. When we dissolve ionic compounds in water, the 2 ions break apart and float around on their own. Okay, so that's something different between ionic compounds and covalent compounds. A covalent compounds, all the pieces stay together, or where the pieces are the atoms. Okay, all the atoms stay together, bonded together as one unit. So phase symbols. So what I just drew up on the board right there. You can imagine that that is the hydrolysis of water. So what I can do is I can take water and I'm going to go ahead and use the balanced equation, and we are going to continue to use balanced equations moving forward. I may need your help balancing them correctly. All right. But if we think about hydrolyzing water, so I can take water and I can put electrodes in it, and out of that water, what'll happen is I can electrolyze it and I get oxygen out and I can get hydrogen out. I can separate them, okay? Which is really cool if you were to think about you were going to make a spaceship and you were going to try and go someplace, right, where you had an abundance of water. As long as you had plenty of energy, either through fusion power or through solar power, you could make your own oxygen as long as there was water around. Okay. And if you, a Martian, if you read The Martian, I can't remember how well it was emphasized in the movie, but if you read The Martian, he was doing stuff like that. Okay. As long as he had enough water, he didn't have to worry about running out of oxygen, enough water and enough sunlight. If you remember for The Martian, there was a problem with this dust storm as well. So you would, in this case, you would start with liquid water, and when you hydrolyze it, you would get gaseous oxygen and gaseous hydrogen. Okay? So we put these symbols in so that we know what the states of matter are here. And like I said, that's important. If we think about sodium chloride, so this is table salt. Table salt is a solid, but if you take that table salt and you put it into water, or if you just happen to leave your windows open in the particularly humid Virginia summer, you'll notice you get little drops of water where the salt was. It absorbs water, but what you get is, if I dissolve, let's just talk about dissolving this in a glass of water. It is going to break up into sodium ions and chloride ions. Okay, so it would look like that. This is what we call an ionic equation, and I'll talk about that more at the end. I could also write it like this if I was writing the molecular equation. Okay, and as chemists, we would recognize that this is an ionic compound, and it says aqueous. That means this is really what it looks like. It's not a sodium and a chloride stuck together floating around in water. It's sodium ions and chloride ions floating around in water separate from each other. Questions on what those things mean? So we used what? We use the solid, we use the liquid, we use the gas, we use the aqueous. So we're going to label those things, and I'll continue to label those as we move through the lecture and as we do other things in the class. Okay? All right, then I'm going to, unless there are questions, I'm going to go on and talk about classifying reactions. So we're going to talk about some different types of reactions that happen in chemistry. Jude.
Already specified this, but what makes sodium and
What makes them separate like that?
No, what makes them, what makes them both to be considered aqueous?
Well, I know that, right? So the question is, how would you know that these were going to be aqueous? Okay, how would you know that this was aqueous right here? Well, you know because you recognize this is an ionic compound, right? That's the one way you'd know. And you know that it was soluble in water, so it dissolves in water. So if I was to ask this as a question, how would I do this that would be a fair question for you guys? I would do lithium bromide. Let's do lithium chloride. Okay, lithium bromide's the same thing. Lithium chloride's interesting. It's like table salt, right? Except it uses lithium. Anybody know anything about lithium? Hear anything about lithium ever? What was that? It's used in batteries. That's one thing. Amy Lee has a song about this, Early Evanescence, but you guys are probably too old for Early Evanescence. Anybody listen to Evanescence ever? Okay, there we go. Great. Yeah.
Lithium is also used in it's either schizophrenia.
Right. I think it may be used for schizophrenia and bipolar disorder.
Yeah, I think one of the two.
Yeah, it may be used for both. So it's used to treat that, and it used to be what they would do in institutions where they would treat people is they would take the salt shakers and they put lithium chloride in, hopefully probably mixed with the sodium chloride, so people would get their treatment just eating their food. Now it turns out that lithium has a very narrow therapeutic range, which means that there's not much difference between where it helps you and where it's toxic. Okay, so lithium, if you're getting lithium, your doctor needs to monitor that. It can't be just however much you shake on your food. By the way, Tylenol, you guys are all familiar with Tylenol, right? Tylenol also has a very narrow therapeutic range. Okay, so you're operating at the max dose of Tylenol, and you then take some other drug that has some Tylenol in it. You're probably doing liver damage. So be really careful with your Tylenol.
It smells like nail polish remover.
Does it?
Yeah, if your phone starts to smell like nail polish remover, you gotta go take it to Best Buy and they'll throw it away for you.
Because of the lithium.
Yeah, and it'll explode.
Interesting. Okay, I don't know what that's interesting. I wonder if it's melting down the plastic is what smells like nail polish
They told me that
remover.
was the lithium smell. They're like, that's lithium, and they
Okay.
turn it off.
I'm not sure they're right, but what I may do is maybe I'll later go into this chemistry stockroom and stick my nose in a bottle of lithium chloride, and I'll report back. Okay, ask me again about that. Anyway, lithium. Back to. I'm easy to sidetrack if you hadn't noticed. Lithium chloride. So what the question might be is lithium chloride dissolves in water. Write out the balanced equation for this process, including your phase symbols. All right, so this is a way that I would test that you could pick up on the context clues that which phase symbols you're supposed to use. So lithium chloride, looking up at the board, how many lithiums and how many, looking up at the periodic table, how many lithiums and how many chlorides. So remember the way we figured this out. What's the charge on lithium? +1. +1. What's the charge on chloride? -1. So they have the same but opposite charges, so I'm going to put them in 1-to-1 ratios, right? So lithium chloride, all right? It's dissolving in water, so we can assume, maybe you wouldn't know it was a solid. I probably would specify it's a solid, okay? I'd have to probably specify that. But it dissolves in water, all right? So if I write lithium chloride over here, what phase symbol do I put with it? AQ, right. Dissolve, that's what dissolve in water means, okay? Or you could have written, the way I phrased the question, that's the molecular equation. You could have written the ionic equation like this. I didn't specify which one you use, so both of these would be correct for that sort of question. Okay, does that help? So that's the only way that I would really ask you a question, expecting you to know those context clues. We are going to have, not today, but next lecture, we'll probably be talking about solubility. And there are some specific facts about solubility you're going to have to memorize. And I haven't talked to my other colleagues to see where they put the bar for that. So I'm going to need to talk to them first and see how much. It will surely be less than I had to memorize in college. So we're going to let's go other questions actually before I go on to classifying reactions. All right, so let's talk about classifying reactions. All right, so classifying reactions, we're going to have 4 types of reactions we're going to talk about here, and then I'm going to add some more later. But we're going to have 4 that you would be able to look at and pick between, if that makes sense. So let me look at my things here. I've got a combustion reaction and there should be another one. Oh, well. I'll have some after. Oh, no, here we go. Got it. Okay. So I've got 2 other reactions beyond this, but I'm not going to mix and match the types. So these are general reactions. So we have decomposition reactions. And your book likes to talk about this as being 2 from 1, or 2 from 1, yeah. Or really, it's more than one from 1, okay? But in the book, it talked about being 2 from 1. And so an example of that would be what I put up on the board right there. So if we're going to have water, right, we can decompose water, we can hydrolyze it, but we're decomposing it to make its components oxygen gas and hydrogen gas. Let me go ahead and get my phase symbols in there. Okay, questions on decomposition? Got one thing, you get more than one thing out. All right, we also have synthesis. All right, so we're making something now as opposed to breaking something down. So synthesis would be 1 from 2. 1 or more from 2, but we'll leave it at 1 from 2 for our purposes. And so an example of this is I could do the reverse reaction there, right? I could take oxygen and hydrogen and put them together to make water. That's my space shuttle reaction I keep bringing up. But to give you a new one, I'm going to give you another simple one for this. We can take nitrogen gas and we can combine it with hydrogen gas, okay, under pressure and at high temperature, and we can make ammonia from this. Let's see if I balance that correctly. Yes. Okay. And then this is a gas. This is a gas. I think we're going to call that a gas too. That's going to be a gas. You can dissolve that. You can dissolve ammonia in water, so it could be there's water in this process. This is called the Haber process. And so when you think about all the plants and farming that goes on that provides the food we eat, the Haber process is really important for that. If you just eat meat, your meat, whatever you're eating, ate plants, okay? So this is super important for us supporting as many humans on the earth that we have, because there isn't, this is called fixed nitrogen. That's nitrogen that plants can take up to grow, okay? And this is nitrogen in the air, and the air around us is like 80% nitrogen. But it's got that triple bond, right? When we think about nitrogen, we've got that super strong triple bond there between the 2 nitrogens, and it's really hard to split apart. All right? So to have enough nitrogen out there for plants to grow on, plants can't do this. They can't split that apart. All right? So just to have enough of this accessible nitrogen, we have to run the Haber process. We have to make it into ammonia, okay? And then usually then you take it from ammonia and you make it into some other form of nitrogen where they're split apart. that you can actually spread as fertilizer. I think I asked whether people really work with ammonia much. Ammonia smells really bad, okay? So they're not often using this directly as fertilizer. It's also a gas, so it kind of floats off when you put it on the soil. Questions? Oh, but the point here is it's a synthesis. We've got two things, and we make one thing out of it. Okay? So we're building something up. All right, those are pretty straightforward. I may have got myself in trouble here by not. I did. All right. We'll start a new one. Another one of these we call single displacement reaction. This one's a little more complicated. Single displacement. Okay? And so for single displacement, what I have is I have kind of lonely element. One element by itself switches partners with another element with an element that has a partner. So if you look at your book, it has these cute little pictures of people dancing. And we're going to contrast that with double displacement. But both of these involve switching partners where we think about partners as atoms. So an example of single displacement is I have magnesium. That's going to be a solid when it's all by itself. Plus HCl. We're going to call, well, let's call that a, let's be fancy and call it a liquid. Okay, we won't have this going on in solution. And what that's going to make is, now I'm going to make it aqueous. You don't need to worry about that. Let's say it's dissolved in water for this reaction to happen, and it could be, sort of. And that's going to make magnesium chloride, which is a salt that will dissolve in water, plus hydrogen gas, okay, which would bubble out of whatever our solution was we were doing this reaction in. So we've got magnesium plus hydrogen chloride to make magnesium chloride plus hydrogen gas. The magnesium has no partner. The hydrogen does have a partner, as in the chloride. The magnesium takes the chloride from the hydrogen, and now the hydrogen's all alone. Single displacement. Does that make sense? Okay. And then double displacement. We each cations, these are cations, but the ones in front, right? It's not a cation yet, but each metal or hydrogen is kind of on the metal side, right? Okay. We're not really going to count the metal, but yes, Tyler.
The equation isn't balanced.
It is not balanced. Thank you. So let's see. I've got two chlorides, right? So I'm going to put a 2 over here. Now I have 2 hydrogens and 2 hydrogens. I have 1 magnesium and 1 magnesium. Look good? Okay, great. Thank you. I appreciate that. All right, so then let's go ahead and think about double displacement. So I've got lead. I'm going to make this lead 2. It could be lead 2 or lead 4. And so that means I'm going to need 2 nitrates to go with it. All right? Lead nitrate, which will be aqueous, plus 2 sodium iodides, which are also going to be aqueous. All right? And that can go to make lead iodide, which is this yellow solid, and then 2 sodium nitrates, and which are going to be aqueous because they dissolve. All right, so we have the lead and the sodium are swapping partners. Over on the reaction side, the sodium was with the iodide, and the lead is with the nitrate. On the product side, now the lead is with the iodide, and the sodium is with the nitrate. Double displacement. They both displaced each other and got new partners. Questions? Okay. Let's go ahead and practice those real quick. So let me give you a couple. I'm going to just go ahead and be writing these. I'm going to write 4 reactions down, and I want you to classify them as single displacement, double displacement, synthesis, or decomposition. Okay, one of those 4. So you go ahead and classify them while I'm writing them down, and then we'll go over them. So we've got tin. Tin can react with bromine. It's going to be bromine gas. Oh no, bromine's a liquid at room temperature. Bromine liquid to make tin bromide. Okay, and as a bonus there, tell me what the charge is on the tin on the right-hand side if you get done with everything else. Your next reaction to characterize, classify, is going to be HBr, so hydrobromic acid. We'll talk about what acids are later. We'll have plenty of acids to talk about. Plus, oh, tin again. Tin solid goes to make tin bromide plus hydrogen gas. So what kind of reaction is that? Another one is we can take hydrobromic acid and react it with sodium hydroxide to make sodium bromide plus water. And then finally, we could have magnesium sulfide, which is a solid, react with water, which is a liquid, to make magnesium oxide and hydrogen sulfide, which I've talked about before is the smell of rotten eggs. It's stinky. So remember, we're looking for, is it decomposition, is it synthesis, is it single displacement, or is it double displacement? I'll give you one more minute, and then we'll go ahead and label those. Remember that I post these notes, so for something like this, you're frantically writing it down for most of the time. Write down the equations. Take some time and make sure to give yourself some time to read this. Maybe write down what you think the answers are, and then you go back to the notes I posted to copy down the reactions. Okay, let's go ahead and look at the top one. So I have tin reacting with tin bromide to make, or tin reacting with bromine to make tin bromide. What kind of reaction is that? Synthesis, right? I've got two and they become one. So this is going to be synthesis. All right. Bonus question, what was the charge on our tin? I heard one answer. Anybody else want to give me one? What's Tyler?
+4.
It is +4. I've got 4 bromines. Each bromine is a -1. So this has to be +4 for this to be neutral. Okay. By the way, all these problems are from the back of your book, but these are actually the even problems. I didn't want to steal your practice problems from you. Okay. The even problems when they don't have the answers. How about this next one? It's not 2 makes 1, and it's not 1 makes 2. That was, what was that? Single displacement. So I have tin all by itself, right? And then tin gets a partner, and I have hydrogen with a partner, and then it is all by itself. Okay, so single displacement. How about this one right here? Yeah, this one's double displacement, okay? I have hydrogen and sodium, both have partners, and then they swap partners when we go to the other side, right? Okay. Water is, the way I've written water here, we could write water, we're always going to write water like that, right? That's how we write water. But water you can think of also as HOH. If that helps you see that a hydrogen got a partner. It got a partner in that OH. Does that make sense? It's not as clear what the partner is there, but it's clearly not alone. So that's going to be double displacement. Okay, and then finally we've got down here, what is this? That looks like that's a double displacement, right? We've got magnesium has a partner, hydrogen has a partner in HOH, right, for water. And then hydrogen has a new partner, sulfur, and magnesium has a new partner as in oxygen. All right, so when I copied these down last night out of the back of your book, clearly they didn't do a decomposition there, right? 1 makes 2. But this is going to be double displacement again. All right, but you will have examples of all of those in your homework for Monday. What question, are there questions on this? All right, so then let's go ahead and talk about a couple other reactions. So another type of reaction would be metals reacting with nonmetals. That's not really, I mean, that's just how we're going to describe it. Okay, metals reacting with nonmetals. All right, so what we can think about is when you have metals reacting with nonmetals, we're going to make an ionic compound. All right, so the example I found in the problems in your book was strontium reacting with bromine. Okay, strontium's up here on the periodic table. It's number 38, or it's on the periodic table in front of you. What's its charge? For strontium, 38. Tyler? So there we go, +2, great. +2. All right, it's going to be +2, so that means bromine is -1. I've got to put 2 bromines with a strontium. All right, but the point here is they make ionic compounds. Okay, and so this is where, remember I had that, what was it, on Monday I got a little confused with this 2.0. Remember we have the 0.5 for polar bonds, right? When we talked about differences in electronegativity. And I talked about 2.0 being ionic. This is where that comes in, okay? I'll explain my confusion when we talk about acids, all right? Because that's where I was getting confused. But if we have a difference of 2.0, it's ionic, and one of the elements takes the electron from the other one. So in other words, what goes on is the difference between, I don't have the chart up, but the difference here is that bromine and their metals don't have a very big, they're not very electronegative, right? They want to give up electrons. They don't want electrons. So strontium is going to give up its electrons to bromine, and so we end up with an ionic compound. Bromine takes the electrons away. Does that make sense? Okay, so we're going to make ionic compounds whenever we have a metal reacting with a non-metal, or generally. I wanted to put states on here. Strontium is going to be a solid over here, and then this is going to be an ionic compound. I'm going to call it it's in bromine liquid. I'm going to call it a solid. So we'll get like the ionic compound in the bromine liquid. All right, if we had water around, if that ended up being dissolved in water, it could be aqueous. Go ahead and do this one. Same thing, sort of thing. You're going to have to think about charges though. So we've got sodium reacting with chlorine gas. Chlorine gas is nasty, by the way. It looks like I didn't, no, it is balanced. Okay. The reaction above is balanced. Balance your equation once you're done too. If you have time.
Sodium chlorine, CO2. But or NaS or what do you ask? How do you complete the reaction?
Okay, let's go ahead and look at this. So the charge on sodium is what? +1. What's the charge on chlorine? -1. So they're going to be 1 to 1, right? So I'm going to write sodium chloride. We'll assume that this is like the sodium chloride crystals on the outside of the metal because we exposed the gas to it. You guys may not care about that, but I'm going to call it a solid because I don't have water around. The problem with well, let me finish this and then I'll talk to you about the problem with water. All right, now I need to balance it, right? How many chlorines on the left? 2. So I need to make 2 on the right. And then now I have 2 sodiums on the right, so I need to make 2 sodiums on the left. All right, so that's what I would do to balance that. Questions? Yeah. Oh, whoops, that's on a subscriptive 2. No, thank you. My problem was, oh no, that isn't I just confused myself at the board. I did have it balanced correctly. But that's not, this subscript is not a 2, it's a solid.
On the left.
On the left, that is a 2.
That is a 2?
Yeah, that's chlorine gas. That's how all of our halogens, so the halogens are all those things, fluorine, chlorine, bromine, iodine, they all exist as 2.
Okay, so we don't carry it over to the other side more.
You don't carry the subscripts, right? So whenever we have a chemical reaction, we have things that are bonded together on this side, and all those bonds could change. They don't all have to, but some or all of those bonds will change, and then we'll come over to this side, and we'll have new partners for everybody. Yes?
So if the chlorine were to remain a gas, we carry the 2 over?
Right, if we had chlorine gas on both sides, yes. Okay, so an example of that, let's talk about an example where you would carry things over together. Let's do, okay, this is a different example. It is not metals reacting with nonmetals. All right, but if we were thinking about, well, actually, let's go up. We'll have an example up here. Here we go. Here, I had for this reaction, for double displacement, the nitrates actually stayed together. The NO3s, that's one of our polyatomic ions, that all stayed together and came over here. Okay, it may not be obvious because it doesn't have parentheses anymore, but that's just because there's only one of them. Does that make sense? So there, they stayed together. So it doesn't mean everything doesn't, all the atoms don't have to rearrange, but some atoms will rearrange when we go from one side to the other. Otherwise, nothing's happened. All right, so we'll get rid of this. Other questions? Good questions. Okay. All right, so let's talk about another type of reaction, a combustion reaction. Now you've seen this a bunch of times because I keep using it. Combustion reactions are really important for all sorts of things we see in our daily lives, right? I'm a biochemist, so really important for biological reactions because your body does these, although it does these in kind of indirect controlled manners. It's important for how your car, you're burning gasoline in your car. Your heat is burning natural gas, unless you have electric, but combustion reactions are really super important. So one example of a combustion reaction. So if we talk about the sorts of things we do burning, I've already shown you this reaction before, but this is natural gas. We can combine it with oxygen. And when we combine it with oxygen, what we get is we're going to get carbon dioxide plus water. Okay, so combustion reactions are these are reactions where we combine something with oxygen. All right, oxygen reacts with something. That something could be various things. I've done these hydrocarbons a lot. The combustion reactions are also these reactions where we have to use the something over 2, right? Sometimes we end up with odd numbers because oxygens come in 2s, and sometimes they're reacting in terms of odd numbers. But so what we've got here, I've got this, everything's a gas here. I'm going to assume that after this is reacted, that the water is so hot it's still a gas. You can prove this reaction works to you, actually. If you've got a gas stove you're working with and you've got like a glass or a glass plate, be careful not to burn yourself. But you could turn it upside down on top of the stove and you'll see it fog up, and that's the water condensing on it. Okay, so be careful, don't burn yourself. But that's one place you see that. So let's go ahead and balance it. So we're combining with oxygen. Let's balance this one really quick. I have 1 carbon on the left and 1 carbon on the right, so I'll leave that like that for now. I've got 4 hydrogens on the left and 2 hydrogens on the right, so I'm going to put a 2 there to fix it. And then, sorry, we're beyond the balancing class. Please practice these if you need to. But I've got 2 oxygens here, right? 2 times 1, 2. I've got 1 times 2, 2 here. I've got 4 oxygens on this side. I don't have to use one of those dreaded 2 over 2 things, or not 2 over 2, but something over 2 things, because I have an even number of oxygens over here. 2 oxygens, 4 oxygens, it's balanced. Okay? And what you should do is use the process. I'm whipping through when I balance here at this point. But that's the process you should think about using for balancing, right? Bounce back and forth, pick off things that aren't, leave oxygen till last usually. Just so you think that we're not always taking, this is a hydrocarbon on the left here. Just so you think that, don't think that carbon's always involved. We can have other oxidation reactions. So calcium, metal, could react with oxygen gas. And that's going to give us calcium oxide. What's the charge on calcium? +2. It's in that second column from the right. So oxygen is -2, okay? So I'm going to end up with calcium oxide 1-to-1 ratios because they're the same here. And this would be a solid, okay? And then what I've got 1 calcium on the left, 1 calcium on the right, okay? I've got 2 oxygens on the left, 1 oxygen on the right. So I guess the way I would do this is maybe I'd go 1 calcium, 1 calcium. Now I've got 1 oxygen, so I'd have to do a half here. Okay, that's what I'm doing in my head. And then I would go ahead and rewrite it where I multiplied everything times 2. I'm not going to write my 1s. I forgot, this is a gas. That's a gas. Those are oxidation reactions. All right. When iron turns into rust, that's an oxidation reaction. I just haven't written it here. Okay, questions? Then let's try, or that's an oxidation, it's a combustion reaction, sorry. Same thing, but we'll say a combustion reaction, okay? One final thing that we have already talked about, so I've got 2 minutes here to cover it. What I want to do is I want to cover molecular and ionic equations. I think I'm going to actually go back up here where we talked about them. So we have 2 ways of writing these. When I have something that is aqueous in solution, I have 2 ways I can write it. And if I write it like this is a molecular equation. And if I write it like this, where I break the ions up, this is actually more what it looks like. I see a problem here. This is more what it looks like in solution. It's those ions floating around separately. This would be the ionic equation. So I take that, if I have, for an ionic equation, you take wherever you have AQ listed next to an ionic compound and you break it into its ions. That's what's going on. And that could be going on the other side of the equation as well. We won't worry about that just yet, but that's going to be Monday or Wednesday of next week. But let's go ahead and do the same thing up here again. Which of these is the ionic equation for the sodium chloride? Top one, right. So this is an ionic equation. And this one is then the molecular equation. Questions on knowing the difference between the 2 of those? Okay. What we're working towards with that, you don't need to worry about it too much right now, is net ionic equations is what is going to be coming up for that. You guys have a great weekend. If anybody has questions, feel free to come down and talk to me about them.